2 is actually going to kind of start us, it's kind of a big fundamental chapter, and we start talking about motion, right? That's our whole basic premise really for this class, right? Is how things move, why things move, all that kind of stuff. So we're going to introduce things like motion, velocity, displacement, distance, all that kind of stuff, and that's what we're going to really start looking at. But to introduce that, we're going to look at some diagram stuff and all that. So motion is everywhere, right? Everything we do involves motion. And our eyes, like we are wired to look at motion, right? When something moves, we want to see what it was, right? Our eyes, we are just literally wired to see what is it that's moving, okay? So we're wired to detect motion. We are more attracted to moving objects than to stationary ones, okay? We've got to start kind of reframing the way we think about motion, right? And the way we need to be thinking about motion is that when an object is moving, that means its position is changing. So when we say its position, that means like where it's located, right? So when it's in motion, that means it has a changing position. It's covering some sort of ground, right? Do we agree with that part? So what do you think position is probably measured in? What do you think position might be measured in? What's the unit for position? Meters, right? Because it's a distance that our object is covering, all right? Okay, there's a lot of different types of positional changes: straight line motion, circular or circle motion, and then arc motion. So what's another word for arc type motion? Something that goes up and comes back down? Okay, it does make the shape of a parabola. What else? What'd you say? Okay, not quite back and forth. If I launch something up into the air, it does involve gravity. It's called a projectile. Have you heard that word before? Projectiles are objects that follow an arc-type path. So that means they move both horizontally and vertically through the air, and then they reach the ground on the other side, right? Projectile-type motion means it's just something that goes up and comes back down. Circular motion could be anything that moves in a circle. Horizontal, it could be a vertical circle. It could be even things that are orbiting, right? Like planetary motion is considered circular motion. So we're going to look at all of those different types. We're going to start and spend a majority of the first semester on straight line motion. Okay, we'll touch on projectiles, but we will also spend a lot of time on straight line motion. So what do you think straight line motion probably means? Just objects that are moving in straight lines. Those straight lines could be purely north, purely south, but they could also be like at an angle, right? As long as it's a straight line. It's just something that's moving either horizontally or vertically, not both. Does that kind of make sense? So it's moving either horizontally or vertically, but not a combination. Okay, the last type of motion is considered back and forth motion, and that's called simple harmonic motion. That would involve things like pendulums. Do you know what a pendulum is? Right, it swings back and forth. Okay, it's in like a grandfather clock or the little decoration that sits on someone's desk, that bounces back and forth. Okay, simple harmonic motion. Okay, simple harmonic motion. That's also any type of vibration is considered simple harmonic motion. Those are things that are repetitive, simple repetitive motion. Okay. When we picture straight line motion, we always relate it back to both a place and a time. So how long did it take and how far did it go? Those are the types of questions we're going to be answering here. So this is as simple as motion can get, right? This object moved from point A to point B in a straight line motion, right? That's literally as simple as it gets. Something moved in a horizontal straight line, and we're going to be able to diagram that and figure out what that's going to be. Okay, when we draw, I want to go back one more time. When we look at motion, we're often going to draw a diagram to represent that motion. That doesn't mean we have to draw the objects, but this right here, even that simple thing could be considered a motion diagram, right? You're going to see me draw lots of really intricate art with physics, okay? I'm being sarcastic with that because I'm the worst artist, okay? But I can draw a straight line sometimes, okay? So you're going to see me draw different motion diagrams to help us determine like what is happening with our motion and give us a little bit better picture of that. Okay? So when we start picturing motion, when we start writing out diagrams, we're going to use a coordinate system. Do you know what I mean when I say coordinate system? Right? With an origin, with the quadrants, right? With positives, negatives. But when you look at your motion, you're going to pick the origin. You get to choose where the origin is. And now when I say that, I'm going to give you a tiny little example here, okay? Let's say we've got somebody standing on top of a cliff or a hill or something. Throws the ball over the cliff, okay? This is, for some reason, an example we use a lot in physics, okay? They're up tall on something, they throw something, we want to see how far it goes, okay? When I talk about this motion, I don't like to choose the ground, right? If I'm going to put this on a coordinate system, I don't like to choose the ground as the origin. I like to place my motion on the coordinate system where my motion starts from, okay? So I like to place where my motion begins from at the origin. Does that kind of make sense? I get to choose where I kind of overlay my coordinate system on my motion diagram. And I always choose the origin, or 0, 0, to be at the point of the start of my motion. So that means if my object's moving, it's moving in the positive direction, it's moving forward, but it's going to end up negative. My vertical direction is going to end up negative. So what's that mean? It's going to end up below where it started. That negative tells me I'm going to end up below where it started. That's the reason I draw my diagrams that way. Some people always choose to make their motion diagrams with the origin like at the ground. I just prefer not to do it that way. I'll show you how we can do it either way, and you can choose whatever works best for you. But you'll always see me pick the origin to be the start of the motion. Okay? When we start looking at straight line motion, here's a couple vocabulary terms we've got to know. Okay? We got to know the difference between distance and displacement. Okay? Distance and displacement are two ways that we can kind of measure an object's position change. Okay, distance and displacement. They have two different definitions. Distance is the total amount of length that we covered. The total amount of length that we covered. Okay? So if I walk 3 meters this way and then 3 meters back, how much length did I cover in total? 6 meters. Okay, but now here's where it gets a little bit different because displacement means something different. Displacement means how far you ended up from where you started. So how far you ended up. That's a really important definition for us. How far you ended up from where I started. So if you think back to my walk, I walked 3 meters that way, 3 meters this way. What's my displacement? 0, right? It appears that I did nothing, even though I went there and back, okay? So when you run around the track, what's the distance you travel? 400 meters, but what's my displacement? 0, okay? So there's a difference between distance and displacement, okay? Sorry, I don't know why this word is in here wrong. This is the variable for displacement. I didn't know that was in there. Oh, okay, cool. The variable for displacement is x. It's x, okay? Why do you think maybe it is x? Any ideas? Yeah, because it's on the x-axis of our coordinate system, right? It's on the x-axis. Now, what will happen if we were talking about vertical displacement? Things going up and down. What do you think we might label it then? It could be a y. So I'm going to go ahead and have you add in there. Displacement will be labeled with either an x or a y. Okay? X or y is how we label displacement. And so what do you think the unit is for displacement? What do we say it's going to be measured in? Meters. Measured in meters. Okay, I don't know if that's on your sheet or not, but we're going to add that in there. Measured in meters. Okay? All right, displacement is what we call a vector quantity. Have you heard that word before? A vector? Maybe, okay, a vector quantity. A vector quantity is any type of measurement that has to have both magnitude and direction. Magnitude and direction. So that might seem like, well, I don't even know what that means, okay? Magnitude is like the number, and direction is the direction, okay? It could be north, south, east, west. It could just be positive, negative, right? But it's got to include a direction with it. So let me give you an example of a vector quantity. If I say I went 12 meters south, there's my magnitude, there's my direction, okay? Even if I said I had a displacement of negative 10 meters, that's my magnitude, that's my direction. Okay, so what would be a situation in which we have a displacement that is negative? anytime we go backwards or down. Okay? You need to understand when we talk about negatives here, we're not talking about the numerical value, right? The negative doesn't apply to the number. It applies as the direction. Okay? So negative means that we're moving down, we're moving backward, we're moving south or west, right? Because on a coordinate system, on a coordinate plane, that's the negative, negative, positive, positive. Do we agree with that part so far? So this is north, east, south, and west. So south and west are our negative directions. Are we in agreement with that? We feel comfortable with that use of negative? It has nothing to do with a numerical value. I can't travel negative 10 meters, right? There's no way I could travel negative meters, right? You're traveling or you're not. So the negative only tells us direction. Are you okay with that? Okay. So when we have vector quantities, any sort of vectors that we have, there's going to be several different types of measurements that we talk about that are vectors. Displacement is the first one. Vector quantities are represented with an arrow that's drawn to scale. So there's a couple different ways we can draw to scale. But when I say drawn to scale for us, I mean basically a proportionate scale. Okay, there will be times where we get out a ruler and we develop a scale and we actually draw it, right? We might say 10 meters is represented by 1 centimeter and I actually draw that scale. But for right now, when I say I walked 10 meters and then I walked 2 meters, are those vectors drawn to scale? No, why not? Because it's the same length as that one. Right? If I'm going to draw them to scale, that means if I go 10 meters, then 2 meters, that's more a little bit more appropriate. Okay? We need to do that because it gives us a better idea of where we're going to actually end up. Okay? When we draw an arrow, we always draw them in the direction of the motion. In the direction of the motion. And I think that should seem obvious, but you would be surprised. Okay, so we draw that in the direction of the motion. So if it says we're going west, I'm going to draw my origin. There's my vector. It's going to the west, right? So you draw them in the direction of the motion. Okay, and to a reference. Okay, so vector measurements have to have a magnitude and a direction. A scalar measurement does not include direction. It does not include direction. So scalar is any type of a measurement or a quantity that only is the number. That does not require a direction. Okay? Distance is an example of a scalar quantity. And let me kind of explain to you why that is. Distance is an example of a scalar quantity because when I walk 3 meters and then I walk 3 more meters, I have walked a total of 6 meters, right? That's the magnitude of my distance. But can I tell what direction I walked? Why not? I walked 2 different directions. So there's no way I can give a final direction there, right? So distance does not include direction. I will tell you, we will use displacement 97% of the time. Okay, we don't deal with distance a lot. Most of the time we deal with displacement because we need the direction that goes with it. Time is a scalar, temperature is a scalar, because with temperature, the negative actually has something to do with the number, not just the direction. Okay? So let's talk a little bit more about vectors. How do we draw vectors? With what? An arrow. Okay, so we can start drawing vectors and adding our vectors graphically. What's called graphically. We draw them to the scale, either a proportionate scale or an actual scale. And we use what's called the tail to tip method to add our vectors. Okay, so what that means is, let's say I start, right? Here's where I'm starting from. And I walk east, then I walk north, then I walk east again, then I walk south, then I walk, then I walk west, then I walk south again, right? I do all of those things. But I'm not just saying, I'm not just drawing it like this, right? I can't just say I went east, then I went north, then I went east, then I went east again, then I went south, right? If I draw my vectors like this, it gives me absolutely no clue where I'm going to end up. Would you agree? Right? Drawing vectors like this gives us a path. And now we know here's where I ended up, here's where I started. And it allows me to figure out how far am I going to be from where I started, right? I'm going to be able to calculate that value and figure out exactly how far am I from where I started. Does that kind of make sense? So when we draw vectors, we add them one right after the other. We don't restart at the origin, right? We add them one after the other. That's called tail to tip method. And it's really, really, really important. Really important. Okay, I will start to see you. There will be people that do this. We go east and we go north, and we'll see people do that. Okay, but this doesn't tell me where I am from where I started, right? I started at my origin. I started my path right here, but like I don't know where I'm going to end up because it's not taking me anywhere. All right, so I've got to make sure that we add them tail to tip. That way I can figure out where am I from where I started. Okay, so that's just going to come up as we go through that. All right. We always draw them in the direction of the motion. We kind of mentioned that. Okay. When we add vectors graphically like that, when we add them in tail to tip, we have one final vector that's called a resultant vector. A resultant vector. It is the graphical sum of all of the vectors that we just drew. The graphical sum of all the vectors that we just drew. Okay, it's basically the final portion of our chart, and it really tells us where we are in comparison to where we started. Okay, so when we draw a resultant vector, it goes from the origin to the tip of the last vector. That's really, really, really important. Okay, so maybe highlight that, circle that, but it's really, really important. The resultant vector starts at the origin, and it goes to the tip of the last vector. Okay, because it tells us where are we at in comparison to where we started. So let's go ahead and try an example here. Oops. Do I not have a graph on there for you? I do? Okay. Oh, I'm sorry. Here we go. Okay, so let's see this one. My runner starts at the origin and runs forward 2 meters. So first of all, let's figure out, do we think they're running horizontally or vertically? Horizontally, right? They're moving horizontally. Okay, so we're going to go forward 2 meters. Which direction do you think we consider forward? To the right or to the left? Right. To the right, right? Because this is the positive direction. So forward 2 meters. I'm going to draw that vector. Then I go backward 6 meters. So now do I start over and go backward 6? No. I start directly from where I ended. So I'm going to go 1, 2, 3, 4, 5, 6 and draw that vector. Then I'm going to go forward 4 meters. 1, 2, 3, 4. I'm actually back at where I started. And then it says I'm going to run forward 5. So 1, 2, 3, 4, 5. So I'm going to end up right there. My resultant vector here, okay? I'm ending up right here. So my resultant vector is going to actually be a copy of that last one. From the origin to the tip of the last vector. So that tells me, what is my displacement here? What's my final displacement? 5 meters in what direction? 5 meters? East or forward. Yep, that's fine. Uh-huh. Yeah, you could just put, honestly, you could just put it like underneath if you want to. On yours, that's fine. It's much easier to draw resultant vectors, or honestly, it's almost pointless to draw resultant vectors when it's just one dimensional like this. So we're going to start looking at them going in multiple directions, and then a resultant will make more sense. Okay? So what's my distance? What's my distance covered here? 17. My distance is 17, and do I include direction on distance? No. Right? No distance. So my displacement here, my x would be plus 5 meters. Right? If it's positive, and we know forward is positive, you can leave it off. Honestly, if you leave it off, we assume positive, and so that includes our direction. You can put it on if you want. But let's try another one here. You will need your calculator for this one. So why don't you grab your calculator as we start to prepare on this one? Okay, This one says I went 11 kilometers north, then 11 kilometers east. 11 kilometers north, then 11 kilometers east. So I want you to figure out what's my scale going to have to be on this graph. By twos. Okay, so let's see here. I'm going to start at the origin. I always kind of draw a dot where I start at, right? I'm starting at the origin. And I'm going to go north 11. So there's 2, 4, 6, 8, 10, 11. So I'm going to creep into that up there. Then I'm going to go east. Sorry, is that one kind of hard for you to see? I'm going to go east 11. So 2, 4, 6, 8, 10, 11. About there. Okay, and I like to go ahead and label those sides. That was 11 kilometers. This was 11 kilometers. And so now if I want to find my resultant vector, where does it need to go from? Right, I'm trying to find out what's this distance right here. Okay, so my resultant vector always goes from the origin to the tip of the last vector. So that red one there is my resultant vector. It is giving me the graphical sum of those two vectors that we drew. How is it that I could find that value? Can I calculate that red line's value? Using what? Slope. Okay, I could use slope, but what does this make right here? A right triangle, so what could I use? Pythagorean theorem, right? A squared plus b squared equals c squared. We will use a lot of trig, so SOHCAHTOA. But for right now, I think you could do Pythagorean theorem, right? Do you know Pythagorean theorem? A squared plus b squared equals c squared. Let's do that and solve for this value. How far am I from where I'm starting? Okay. Okay, so that's what I got for my Pythagorean theorem value. Would you guys agree? Yes. The square root of 11 squared plus 11 squared. Right? It's a squared plus b squared equals c squared. So I would take 11 squared plus 11 squared equals c squared. In my calculator, this is what I do. I take square root of 11 squared plus 11 squared. I don't do it in multiple steps. I literally just do second square root of 11 squared plus 11 squared, and I hit enter.
Why is it square root of that?
Well, because I want to solve for c. So to get c by itself, I have to take the square root of that side. So that means I have to take the square root of that side. Right? I got 15 something. Okay. Now, in our final displacement, is this good enough for displacement?
No.
It's got a magnitude, but what's it missing? Direction. Okay, so now can we just say it's 15.6 kilometers northeast? I think that's probably exact enough. The fact that I'm asking that question should maybe lead you to think, no, it's not exact enough. Okay? Because if I say northeast, I could go here. I could go here, I could go here, I could go here. I could go anywhere in that northeast quadrant, and I'm not going to end up to here unless I do it exactly right. So here's what we have to do. We've got to find the angle at which we need to leave our origin. Okay? And then that will tell me how I can get to where I'm ending up. So how do I find this angle right here? We know automatically that it's 45 degrees. How do we know it's 45 degrees? Because our legs of our triangle are, what are these called? I don't know. The sides of our triangle. Okay, the sides of our triangle are the same. Okay, so when we have congruent sides of our triangle, it tells me that angle is 45 degrees. Okay, so we've got one more thing that we've got to do. 45 degrees what? North of east or east of north? How are those different? North of east is here. North of east is right there. So I know it's 45 degrees, so it's the same both ways, but just humor me for a second. North of east would be this angle, because I'm east, and then I go north of east. This angle right here, I'm north, then I go east of north. So that angle, technically, right there, is considered east of north. That's our final answer. We're going to try another one where it's not 45 degrees so we can see it different. Okay? 45 degrees east of north. So let's talk about this angle one more time. When I'm looking at this angle, right, I've got to decide, where is it? Is it east of north or is it north of east? Well, the way I know that is I figure out what axis is my angle touching. Is it touching the north axis, the east axis, south? What is it? Which one is it touching? North. So then I decide, does my triangle, does it swing east of north or does my triangle swing west of north? Right? If I know my triangle's touching the north axis, does it swing east of north or west of north? And the answer is east of north. Okay, so that's how I figured out what angle that was.
So even if it was like 11 kilometers north and then 15 kilometers east.
Yep. So if we had drawn, that's exactly right. If we had drawn a triangle that looked like this, and we still needed this resultant vector, we would calculate that angle we would calculate it with probably sine or cosine now, and then we would still call that angle east of north. Okay? So let's try another one real quick. So you might just do this one to the side, or you can do it, I'll do another one that's south and west. So let's say I go 4 west and 3 south. So I went 4 meters west.
Is this one by ones or 2 still?
This one's by 1, so I'm going to call that 4 meters. That's 3. So this is just a separate problem that you can happen to do on the same graph, or you can do it separate. I don't care. Okay, so let's say I went 4 meters west, then 3 meters south. My resultant vector now is going to go from there. I'm going to figure out how far am I from where I started. I need to find that side of my triangle. Yeah, I know. I didn't pick a very good example. Again, what do we know that one is? A 3, 4, 5 triangle. But I can do Pythagorean Theorem to help find that if I want. Okay? Actually, I want to scratch these numbers. I don't want to make them so easy. Okay, let's call this... This scale's not going to work. But let's just call this 8. Let's call this 10. Sorry. All right, so there we go. So I went 8 west and then 10 south, and we're going to try to figure out what is my resultant vector. Right? What is my resultant vector? So I've got to find the side and I've got to find the angle. So let's do the side first. We use what to find the side? Pythagorean Theorem. I got 12.81. 12.81, right? Second square root of 8 squared plus 10 squared. Okay, in my calculator, I want to try to do it in one step. Okay, so I go second square root of 8 squared plus 10 squared. Then if I want to find the angle, this is not just a 45-degree angle anymore. So I need to find the angle of that triangle. We've got to go to our trig functions. So sine, cosine, or tangent. Okay? You could use any of the 3 because technically we've got now all 3 sides. But here's how I do it. Since I had to calculate this side, what if I calculated it wrong? And then I used it to find my angle. Now my angle's wrong too. So here's the way I always solve for this angle is I use tangent because I know my opposite and my adjacent sides. Does that kind of make sense? So you'll see me use tangent. You are welcome to use any of the 3 trig functions because you have all 3 sides of your triangle now. Okay? So when I'm going to go plug that in to solve for that, do you remember the trick when you solve for the angle? What's the extra thing you have to do in your calculator? Yeah, you got to use second tangent. Okay? So in my calculator, it's going to say tangent -1 of the opposite side over the adjacent side. So 10 over 8. Second tangent of 10 divided by 8. And I get an angle there of 51.3 degrees. Okay, if your calculator is coming out with something different, you might be in radians. In our class, you always need to be in degrees. Do you know how to check that? You check it with mode. Mode right up here, and you need to make sure degrees is dark. Okay, that's really important. Okay, so calculus might be the only thing that you would need to be in radians for. Okay, so I don't know, does he tell you that you're going to switch back? Okay, so here you're going to be degrees. We're almost done. What's this angle have to be labeled? What of what?
West of south.
It's touching It's touching the west axis. So then we decide it's not going north of west, it's going south of west.